So, dear students, let's start the course in time series analysis. Today is the first lecture, Introduction in Time Series Analysis. What we are analyzing is the concept of a univariate time series. Gross domestic product, country population, company's revenue, its profit, all can be indicator Y depending on time. Time can be measured both by years, months, days, and quarters. Most importantly, the time counter should be set to either a date or a relative date on 1, 2, 3, and so on. For time series, its standard derivatives are always considered. Chain gross growth rate 1 plus RT, net growth rates RT, the logarithm of the indicator or the logarithmic scale is also widely used. Logarithmic growth rate or logarithmic return, ROT. Please pay attention to this relation between logarithmic and simple growth rates. In fact, the logarithmic growth rate is just a slightly different scale of measurement than simple growth rates. The same other scale, such as temperature, can be measured in degrees Celsius or degrees Fahrenheit. Also the growth rate. They can be measured on a logarithmic growth rate scale, ROT, or they can be measured on a simple growth rate scale, i.e. RT. The great convenience of using logarithmic growth rates is associated with the calculation of the average value of growth rates. For logarithmic growth rates, the arithmetic mean formula can be used. But for simple growth rates, only the geometric mean can be used. Another important thing is the baseline growth rates. This is the ratio of current indicator Y to the starting indicator Y first. This is very convenient for comparing the accumulated dynamics of indicators of different dimensions. Before proceeding to the analysis of economic time series, we must do 3 preliminary actions. The first preliminary action is to adjust the time series for inflation. Since we have financial indicators, GDP, revenue, profit, and all this is measured in current prices, these indicators are subject not only to changes in real activity, but also to changes in the price level. Because inflation often fluctuates over time, this change in inflation causes changes in variable to introduce in it unexpected changes. And to take into account these unforeseen changes in the model, it is recommended to adjust the forecast indicators for inflation and build a forecasting model separately for inflation and separately for the analyzed indicator itself adjusted for inflation. Otherwise, it is called a constant price indicator. This is almost always recommended unless there is reason to believe that the inflation rate in the historical data period will match the expected inflation in the forecast period. In this case, the adjustment for inflation will not have a significant effect, but will only complicate the calculations. Also, daily and weekly indicators are often not adjusted for inflation, since inflation is usually measured by months. By the way, the choice of the time interval of the analyzed data is also an important task for the researcher. Depending on what result you want to achieve by building your predictive model, you will choose daily or weekly or monthly data. It is clear that the shorter the analyzed time interval, the more sensitive predictive model you will get. On the other hand, many predictive models are built to justify investment decisions for several years, up to 10 to 30 years. It is clear that for such purposes, monthly, quarterly, or annual data are quite sufficient for analysis. To make an inflation adjustment, it is necessary. The first is to calculate on the basis of inflation data an indicator of price level at the end of period, PT. IT is the inflation rate, that is by how many units prices have increased in the national economy on average. So PT is an indicator of the price level. The current price level is the previous price level multiplies 1 plus inflation rate. Recursively substituting PT minus 1 into this formula, we obtain an equation for the current price level from some initial price levels P0 times the product of the inflation rate for all previous periods. The initial price level is always taken as unit, S1. After you have calculated the price level, you need to calculate the indicator in comparable prices, YTR, YT real. This indicator is calculated on the basis of the indicator at current prices, YTN, YT nominal, the nominal indicator according to the following formula. The real indicator is the indicator at current prices multiplied by the price level of the base period and divided by the price level of the current period. P base is the price level of the base period, usually the last year or the last period is taken, because it is convenient to build a model in the prices of the most recent period, because intuitively you understand the value of money of the period in which you live. And then the forecasting model must be built for the indicator in comparable prices, YT real. When you have built a forecast for gamma period, in order to get an indicator in current prices, you must multiply the forecast of the real indicator and the forecast of the price level. Here is the reverse formula applies. In the first formula, the real indicator was calculated through the nominal one, and when forecasting, the inverse formula is used, where the nominal indicator is expressed through the real one. So let's consider an example. In this file, we have data on wages, average wages for Moscow workers in Moscow region. Also in in column C, we has data on inflation. That is, inflation means consumer price index. So this figure means that in January, the inflation the inflation was 2.37% per month. So to adjust the data on inflation, first we need to calculate the price level month end. So here we can see that initial price level is 1, and the following price level is calculated according to the given formula. And now we can adjust the wages to inflation and use the formula that I give to you. That is nominal indicator divided on current price level and multiply on the base price level, that is the price level for the last considered period. So let's go further. The next preliminary action to be done with time series is to decide should they be logarithmic or not. There are two reasons for continuing to work with the logarithm. The first reason is the visual existence of an exponential trend in the data, especially if this trend is accompanied by an increase in variance, as shown at this chart. And the second reason for the logarithm, if the indicator theoretically cannot be less than or equal to the 0. In this case, constructing a model on logarithm allows you to give the indicator the necessary properties. From a mathematical point of view, taking a logarithm means building a multiplicative model instead of an additive model. The additive model is that the time series is decomposed into the sum of the main trend, seasonality, and residuals. The content of the multiplicative model is that the trend, seasonality, and residual do not add up, but multiply with each other. Any multiplicative model is reduced to an additive one by taking a logarithm. That is, if we take the logarithm of y according to the multiplicative model, then by the property of the logarithms, we get an additive models on logarithm of the original variable. That is, in essence, technically, we are mastering the same skill, constructing an additive model, but in the case of a logarithm, we mean that this is a multiplicative model of the original indicator, which better reflects such properties of the time series as an exponential trend, an increase in variance over time, and or its restrictions to only positive values. And if we do not take the logarithm of the indicator, then we use an additive model of the original variable. From experience, in most cases, it is necessary to take the logarithm of the time series, and then it is better to find an error and remake the model of the original indicator than not to take the logarithm initially and then not notice the residual. There are obvious cases where the logarithm will not help. For example, the profit of the company, the profit or net income of the company. It can be negative, and then it makes no sense to take the logarithm. But if the economic indicator cannot theoretically be negative, then in the vast majority of cases, the logarithm must be taken. The third preliminary action to do with time series before constructing a model is seasonal adjustment. Seasonality or unconditional heteroscedasticity is the dependence of the time series on the time of the year, day of the week, month, quarter, in rare cases, it may be on an elective or Olympic 4-year cycle. The seasonal adjustment techniques consists of 2 steps. The first is the selection of the trend of the time series. A trend is a general tendency. It can be selected in the form of some analytical function, but the most convenient is in the form of a centered moving average. I will show you it in an example. The smoothing period of the centered moving average should be selected depending on the seasonality cycle. You can take it equal to the seasonality cycle K, or you can take it equal to 2 seasonality cycles 2K. And you can take the trend as an average of these 2 trends with smoothing parameters K and 2K. For example, if you have monthly data, then K equals to 12. If quarterly data you have, the K equals to 4. And the second step in seasonal adjustment is the calculation of seasonality indexes. They are considered if the average of the deviations of the time series from the trend for the respective seasons, that is months or quarters. And further, we build a forecasting model already for seasonality adjusted indicator. And to obtain a seasonality adjusted forecast, we add the value of the seasonality index for each month to the resulting forecasts. Now let's look at the example. So in this example, after adjusting the variable on inflation, we should to use multiplicative model and to logarithm the variable. So here we've got a logarithm of the variable in constant prices, and when we should adjust it to seasonality. First of all, we construct the trend with a period K equals to 12 for centered moving averages. So it should be an average for the year, starting from January, ending on December. And for that column, for this column named June, we link this trend with the June in the data. Also, we calculate the same average for the logarithmic of the variable from January to December, and here we link it to the July. and copy it down. And now we get a resulting trend as averaging these two types of trends linked with June and linked with July. So here on the graph, you can see the initial logarithmic variable of wages in Moscow and the resulting trend with a centered moving average with a periods of averaging equals to 12, and that is a trend. So next step, we calculate the residuals from the trend, that is Z, and then construct a seasonality indexes as an averaging for the each month of the initial data. So this case is for January, averaging for January. The next cell is averaging for February, and so on, averaging for March, averaging for April, and so on. And for last years, for the following years, we should only copy the initial seasonality index for the all data we have, copy as values. So in column L, we've got the initial price adjusted, the initial variable adjusted for seasonality. That is difference between initial logarithm of variable and seasonality adjusted, and to get an exponent to get an initial variable in rubles per month. So here we see the graph of initial variable Z and the graph on seasonality type index, seasonality index. And at the last graph, we've got an initial variable wages and constant prices, and the resulting variables wages in constant prices seasonality adjusted. So that is a technique of seasonality adjusting. So also I need to note that seasonality adjustment we've looked here is the adjustment outside of the forecasting model. In the modern time series textbooks, you can also find a correction inside the forecasting model. This is the so-called seasonal ARMA, or simply SARMA. Its prediction result will be similar to the above method. However, SARMA is useless if you start making changes to the model specification. This is often necessary when building more complex forecasting models. Therefore, I insist that you should use the seasonal adjustment method outside of the forecasting model. For example, organizations supplying economic data often to do this. They provide both seasonally unadjusted and seasonally adjusted data, so that the user can choose on which indicator he will build his predictive model. Having finished with the three preliminary actions, we proceed directly to the analysis of time series. Unlike cross-sectional data, time series analysis is closely related to the need for detailed attention to two special properties of this data. The first special property is the stationarity of the time series. So time series YT is called strictly stationary if its joint distribution remains invariant to a shift in time. The meaning of this concept is that the form of distribution of a stationary time series is constant over time. Strictly stationarity imposes two stringent requirements on the empirical verification of the stationarity. Therefore, in practice, the concept of weak stationarity has become more widespread. A time series is called weakly stationarity if its mean value and covariance remain invariant to a shift in time. That is, now to check the series for stationarity, it is enough to make sure that its mean value and autocovariance are constant in time. Note that autocovariance with lack of zero is the variance of the indicator. Thus, indirectly, the condition of constant variance is also included in concept of weak stationarity. The second special property of the time series is the presence of autocovariance or autocorrelation in the data. From statistical theory, you know that the covariance of x and y is the expected value of the deviation of x from its expected value multiplies the deviation of y from its expected values. The covariance ranges from -infinity to +infinity. And this is not very convenient. Correlation is normalized covariance. Normalization is done by the division of covariance of the standard deviation of x and y, and then the correlation becomes normalized in the range of -1 and 1. Similarly, for the time series YT, the autocovariance with log L is considered, denoted as cov L, namely the covariance of indicator YT and YT shifted by L lags back. That is some measure of how the indicator L lags ago influenced the current value of the time series. It is calculated as the expectation of the deviation of YT from its own expectation multiplied by the deviation of YT shifted by L lags back from the expectations of the time series. Here the two expected values are equal because it is assumed that this variable YT is already stationary. In general, all such analytical calculations of time series coefficients are made for stationary series. For non-stationary series, violations occur there, and as soon as the non-stationarity of the indicators become obvious, it is not further analyzed in the time series. Similarly, autocorrelation with log L, denoted as cor L, is the correlation of the indicator YT and YT shifted by lags, L lags back, and it will be the covariance between with log L divided by the variance of the analyzed time series. The series is stationary Therefore, the standard deviation of the original series and the standard deviation of the series shifted by L legs back are equal. After calculating the autocorrelation coefficient, the researcher is interested in the statistical significance of this coefficient. Does it differ significantly from zero, or can this difference be attributed only to sampling error? You can test the significance of the autocorrelation coefficient using test statistics, which is compared with the critical values according to the standard normal distribution. Finally, a generalization of autocorrelation coefficient in time series is the concept of autocorrelation function, ACF, which is understood as a vector of individual autocorrelation values with leg L. Two tests are used to test the significance of the entire autocorrelation function of the time series. The first test, the Box-Pierce test, is a little outdated. The second test is an improved one, the Ljung-Box test. Let's consider it in detail. The test statistics QM is considered. Here N is the number of analyzed data of the time series. M is the maximum number of legs by which we test the significance of the autocorrelation function. M can be chosen subjectively. For example, there is an empirical approximation that M equals to natural logarithm of N, but this is not strictly limited in any way. And this statistic has an chi-squared distribution with m degrees of freedom for random independent series. Using this statistic, the null hypothesis about the absence of autocorrelation in the time series is tested. The hypothesis is not rejected if the statistics is less than critical values. Otherwise, if QM is greater than critical value, the null hypothesis is rejected, and it is recognized that autocorrelation is present in this time series. Now, we go directly to the time series analysis models. Any time series that we observe, always there is some sample. However, this time series has some general population that we analyze. This general population arises at the moment of the appearance of the physical quantity that we measure and cease at the moment of the disappearance of this physical quantity. That is, a general population in time series is understood as some unobservable data generation process, DGP. If we use some theoretical model of the analyzed object, we could mathematically formulate this unobservable data generation process and select the correct specification of the econometric model. Then our task would be simply to estimate the empirical parameters of the model. Therefore, the assumptions of the economic theory about the process of data generation become decisive in choosing the specification of a time series analysis model. The modern understanding of the models for the analysis of economic time series has developed as a result of idea of Slutsky, 1923, that economic cycles and crises can be the result of accumulation of chances. Wald, 1954, who proposed the so-called the decomposition theorem, that any stationary time series can be represented as a moving average. Samuelson, 1948, who is in his Foundation of Economic Analysis, said that the dynamics of economic variables should be associated with autoregressive models. And finally, Box and Jenkins, 1970, who developed an integrated approach to the econometric specification of time series models, including moving average and autoregressive process. So based on these four basic works, especially after 1970, when the knowledge of economists took shape in the form of a full-fledged existing theory, it turned out that economic theory predicts, and empiricism in general confirms, that the process of generating economic time series data corresponds to one of three processes. These three processes we need to get acquainted now, and they form a main ground of our time series course. These are moving average process with order k, MRK, and autoregressive process with order p, IRP, and the combined autoregressive moving average process with order pk, ARMA pk, autoregressive moving average process. These three processes we must consider now in more detail. We must learn how to calculate the mean, variance, autocovariance, and autocorrelation coefficients, for what we will have to make some mathematical efforts on ourselves. The first of all, let's recall the basic properties of mathematical expectation and variance, because we will have to apply them when studying the process of ARMA and ARMA. The first property is that expectation of a constant is always equal to the constant. The second property is the expectation of a constant multiplied by a random variable. There is always a constant multiplied by a random variable. The third property is the expectation of the sum of two random variables is the sum of the expected values of two random variables. And the fourth property is the expectation of the product of two random variables is the product of these random variables plus the covariance between these two random variables. Now consider the properties of the variance. The variance of constant is always 0 because it is not a random variable. The variance of a constant multiplied by a random variable is the constant squared multiplies the variance of the random variable. The third property of variance is the variance of the sum of two random variables is the sum of the variances plus two covariances between these two variables. The fourth property of variance is the variance of the sum of a constant and random variable, which is the variance of the random variable itself. This property is a directly consequence of the third property, since the variance of a random variable is equal to the 0 and the covariance of a random variable with a constant is also equal to 0. We need to remember these 8 properties if they are not clear. Then you need to practice deriving these properties from the formulas for calculating the expectations and variance themselves. And further, we will use these properties when studying the processes of AR, MA, and ARMA. So here we have the process of moving average with k order in detail. According to this process, the initial time series variable yt, that is stationary variable, analyzed as the sum of error with log y multiplying on coefficient of moving average process by, sum from e equals to 1 to k, plus error or residual for the current period epsilon t. So all epsilon t is normally distributed variables with average b0 and with variance sigma squared. So our task is to understand the expectation of time series yt, stationary time series yt, and applying the described above formula, we've got that expectation of yt is equal to sum of MR coefficients by multiplies on expectation of epsilon with log y plus constant b0, that is expectation of epsilon t. And then put b0 out of brackets, because expectation of epsilon with log I is also equals to b0 due to its stationarity. We've got the formula 2, the equation 2. Also, we can find a variance of our time series, and according to the described formula, we apply the operator of variance both for 2 sides of our MR process, and we've got that variance of yt is equal to sum from 1 to k moving average coefficients by squared multiply on dispersion of epsilon t with log y plus sigma squared, that is dispersion of initial epsilon t. And put sigma squared out of brackets, we've got the equation 3 for the dispersion. So here we can see the numerical example. And also I would like to note that also k-order moving average process is also possible to determine as a process with a random variable, pure white noise epsilon t with mean 0. With mean 0, not with mean b0, but with mean 0. This means changes in the formula of moving average process by adding here the constant or intercept b0, and in such process, this moving average process as a core is the same as initial moving average process, but its mathematical expectations according to the mathematical properties changes. In its expectations of this yt time series should be equals simple to b0. So now for the process MRK, we will find the autocovariance with lag G and autocorrelation, of course, autocorrelation function with lag G. So here you can see the mathematical calculations from which we obtain. You could analyze these calculations as your homework, but as a result, we've got that for all J that less or equal to K, K is the order of MRK process, we've got the covariance coefficient that distinct from 0, and for all legs with J above K, we've got covariance equals to 0. And by dividing the covariance coefficient on the variance of YT, we've got the formula for correlation coefficient with lag G. So the next mathematical property that we need to know for the MRK process is the representation of this process through the shift operator. We have the original moving average process of order K. Denote the error with lag 1 as some lag operator L multiplies the error without lag. In simplified form, you should think of this operator L as a constant. In a broader sense, L is not a constant. It is really some operator calculated through a differential equation, but its mathematical properties as a regular constant are preserved. If we adopted this notation, then we have lag 2 error is a shift operator multiplied by a lag 1 error, or an operator from the operator multiplied by the original error. And since mathematical operations with an operator are equivalent to operations with a constant, we can write it as an operator squared multiplied by the error. In general, a K-lag error is a K-power shift operator multiplied by the original error. Using this shift operator, it is convenient to represent the original process MRK as a polynomial of the shift operator. This factor in brackets is denoted as BL and is called a polynomial of the shift operator. By mathematical properties, a polynomial can be factorized. A polynomial of this kind, according to the mathematical properties, is the product of 1 minus L divided by Z1, 1 minus L divided by Z2, and so on up to 1 minus L divided by ZK, where Z1, Z2, and Zk are the roots of the following equation formed on the basis of polynomial of the shift operator. The process MRK is called invertible if all the roots of this equation are greater than 1 in absolute values. This is equivalent to the fact that the reciprocals of the roots, i.e. 1 divided by z less than 1. This invertibility is a theoretically important property, because if the process MRK is invertible, then original process Y can be represented as an autoregressive process of infinite order. Let's consider the mechanism of this interpretation. We have the original series Y that is presented as a polynomial of the shift operator for the process MRK. Now let's express a row from here and get this value. We can expand each of these factors according to the formula of the sum of an infinitely decreasing geometric progression, where the initial element of the progression is 1 and its denominator is L divided by Z. In this case, the elements of this progression themselves are Lg divided by Zg, and their sum is the sum of these elements from 0 to infinity. From this representation, it becomes clear why the requirement to divide 1 by z less than 1 become critical for invertibility. If it did not hold, we would not be able to apply the formula of an infinitely decreasing geometric progression, and thus the invertibility would not take place. So applying this formula, we've got the mutual product of k infinite sums, which we denoted as the inverse polynomial of the shift operator b with -1 degree. And now expanding this product of k infinite sums, we can see that the time series yt will be equal to the R infinity process. In general terms, this disclosure of sums is quite difficult to do. So we will see this transition effect a little later in numerical example. So here you can see a numerical example for the given MR2 process. That's a constant of MR process, constant parameters 0.7 and 0.2. And according to the formula, we have expectations of yt and variance of yt. And now we have formulas for covariance and lag covariance and lag correlation coefficients, and we apply this formula to the example and got the result. Now let's consider the ability to represent of this MR2 process in the form of polynomial of the shift operator. So described epsilon with lag 1 as lag operator to the epsilon, and represent it through the polynomial form. And trying to solve the characteristic equation, we've got the discriminant of this squared equation is below 0. That means there is no solution of such characteristic equation, and therefore it means that given the polynomial, given the initial MR2 process, this polynomial is not invertible, and therefore this process can't be represented in the form of R infinity process. Let's take another MR2 process with a different MR process constants. So we've got, applying to leg operator, we've got the following formula in the polynomial of leg operator, and this characteristic equation now has a solution, and the solution is that z equals to -2 and z2 equals to -4, and both in absolute values are higher than 1. Therefore, this MR2 process is invertible, and we can represent it in the form of R infinity. So here is the calculation. We each of this product we can represent using the formula of sum of infinity geometric progression, and by multiplying these two sums, we've got and that is YT, initial stationary time series, is a IR infinity process. Now we turn our attention to IRP process and should consider it in detail. So that is, initial stationary time series YT could be represented as sum from 1 to P. P is the order of IRP process. Sum of RE, that is coefficient of IRP process, given coefficient, and YT with leg Y, that is initial time series with leg Y, plus epsilon T, that is a normally distributed error or residual with mean A0 and variance sigma squared. So as for moving average process, for IRP process, we should understand the calculations of expectations of Y, expectations of time series. That will be simple autoregression process of expectations of YT with log L, that due to stationarity equals to expectations of YT plus expectations of epsilon T, that is A0. And from here we've got that put out of brackets expectations of YT. We've got that expectations of YT is equal to A0 divided by 1 minus sum of autoregression process coefficients. Also the same, doing the same way, we could find the variance of YT, and according to formula, so here you can see some standard mathematical calculations, but the main thing is that for variance of YT, for R1 we could calculate this variance directly, but for R2 and higher IRP processes, we could get only variance dependent from leg covariance coefficient of 1. Here you can see that is correlation YT with leg 1. So therefore it is needed to calculate the covariance with leg 1, 2 for R2 process. At this slide you can see an example that the process of calculating of autocovariance with leg G. for IRP process, and that is arithmetical transformation of this covariance. And for IR1, we've got that covariance coefficient is equals to A1 multiplying on dispersion YT. And for R2, we've got the formula that links covariance with like 1 and covariance with like 0. That gives us understanding that covariance with like 0 is clearly the variance of YT. We've got that covariance 1 is the same formula from the dispersion. And link this formula 7 with the previous formula for dispersion for IRP process on the previous slide. So we've got the resulting formula where we could calculate the variance of YT depending of autoregression coefficients of the model and sigma squared variance of the epsilon t of the noise. And finally, the autocorrelation function of IRP process is just simply coefficient covariance with like G divided by variance of YT. Also, the same is true for IRP process as for moving average process about its representation in the terms of shift operator. And so I would like to note your attention that for IRP process, we've got the different characteristic equation, different than for MR process. Here you've got a minus when considering the MR process. We have got a plus here, but the same, but all other is the same. And about the main terms, about invertibility of IRP process, it is important to say that IRP process, it is called invertible if all roots of these characteristic equation in absolute value is greater than 1, and this invertibility of IRP means that YT, initial time series, stationary time series, can be represented as a process MI infinity. And the second property is that this fact of invertibility proves that IRP process is stationary. So it is necessary to note that all moving average process is always stationarity, but not all autoregressive process stationary. There could be some autoregressive process that's not stationary. And in this case, the invertibility of IRP process proves it's stationary. So in the down of the slide, in the bottom of the slide, you can see the process of transformation of IRP process in moving average infinity process. And following this formula, you can do such transformation by yourself. So here is a numerical example of calculating expectation and variance, covariance, and autocorrelations for a given IR2 process. You could consider this example as your home task and understand it. And here you can see an example of a representation of IR2 process in the form of moving average infinity process. This is also the considering of such example is also for your home task. Now we turn our attention to the combined autoregressive moving average process, ARMA PK process. And here we analyze the initial time series as the sum of autoregressive part of the model and sum of moving average part of the model. Each of these parts was considered in different models early, and the recent part is initial epsilon t, the residuals or the error of the given time period. Of course, the error has a normal distribution with a mean a0 and variance sigma squared. Analogically to ARMA process, this ARMA process can be represented as in the form of polynomial of the shift operator. In the left side, all shift operators according to yt is considered, and in the right side, all operations for epsilon t is considered here. That is polynomial for the ARMA part of ARMA process, that is polynomial of AR part of ARMA process. And if the polynomial of the AR component is invertible, then the process can be represented in the form of MA infinity. On the other hand, if the polynomial of the component MA is invertible, then the process can be represented in the form of IR infinity. And for this reason, the ARMA PQ process, it is common to set that it has three representations. Directly ARMA representation in the form of IR process, and representation in the form of MA process. So these three processes, ARMA, IR, and MA processes, are closely related processes. Let's make some brief summary on processes considered today during this lecture. So the economic cycles and crises can arise as a result of accumulation of errors. This is the result from common result in economic science from Slutsky work of 1923. So then the neoclassical economics predict that economic time series should follow autoregressive moving average process. And the process MRK, moving average with order k, is always stationary process, even if it non-invertible. The invertibility of MRK means the representation of this process in the form of IR infinity process. Process IRP is stationary only if it invertible. The invertibility of IRP means its representation in the form of MI infinity process. And the ARMA PK process has three representations. In the form of MA process, in the form of IR process, and directly in the form of ARMA process. A necessary condition of its invertibility is that polynomials of IR and MA of the ARMA process are invertible. So also we know the Wald decomposition theorem that said that any stationary time series can be represented as the process moving average with order k, and the time series model according to the MRK process is called in the time series science as a linear model. This is the basic model from which the models of time series starts, the linear model of time series. And it means that the time series could be, these time series could represent as the MRK process. So due to mutual invertibility of the process MRK, IRP, and ARMA PK, any stationary time series can be represented as any of these three processes. And non-stationary time series, to analyze it, must first of all be transformed to a stationary form to build the linear model. So that's the main starting properties of the time series analysis that we consider today in this lecture. So the last slide is devoted to the non-linear models. And while linear time series models are dominant in academic analysis, but the current field of the modern scientific research is related to non-linear time series models. So the following non-linear models are widely used in practice. First is the trend stationary models, including Wasserchuk models for interest rates and mean reversion model in stock prices. Second is the process with structural breaks, which we will consider in this course later. The threshold models are widely used to describe the time series with non-linear properties. Fourth is a regime switching model or Markov switching model. The main part of it is devoted to describing an economic cycles of economic activities, business cycles. And of course, in modern literature, there is many other non-linear specifications, including using of neural networks, artificial intelligence, and machine learning systems. So also I would like to know that using a non-linear model often leads to an overfitting the existing data. So it always needs to be compared with a linear alternative based on one of the possible statistics. The linear model is good for describe the considered properties of the data generation process that hidden behind the empirical data. But linear model may be not so good as non-linear model in forecasting. Otherwise, non-linear model very often overfit the initial data, and therefore they can't help us to reveal the data generation process. But maybe sometimes non-linear model has a better predictions than the linear model, and it should be calculated, should be estimated through the non-sample experiment, out-of-sample experiment, and out-of-sample verification of the predictive ability of the used models in your research. So that's all for this lecture. Thank you very much for your attention. And the last slide is devoted to the literature for that course, and then the main book is Royal Tsai, Analysis of Financial Time Series. Also, you can use the book of Verbeek, Путеводитель по современной экономике. So this book is in Russian, but Modern Econometrics by Verbeek you also can find in English language literature. Thank you very much for your attention.